So, welcome back to this session on network analysis. So, we will continue with the second part of network analysis, and today we will start with the second metric that we will get ourselves introduced to, and this is called clustering coefficient. So, the clustering coefficient actually comes from the transitivity property of a network. Transitivity property of a particular network. So, the idea is very simple, that if there are two nodes in the network, say A and B, having a mutual friend say C, then there is a high probability that A and B are also friends in the social network. So, A and C was a friend, B and C was a friend, then there is a high probability that A and B are also friends, right. So, this is what is called the famous transitivity property of a network. Now, this property actually comes from the observation that in many cases, so this probability actually will be higher and higher if you encounter situations like the one that I am drawing. Suppose there are many such common friends. Okay. The larger the number of common friends between A and B, the higher is the probability. So, the higher is the probability that A and B are friends. So, the larger is the number of mutual friends between A and B, the higher is the probability that A and B are themselves friends. So, this idea actually is called the transitivity of a particular social network, and this transitivity can be quantified using something called the clustering coefficient that we will define now. So, the clustering coefficient can be measured for each vertex. So, it is a vertex centric measure. So, clustering coefficient is a vertex centric measure. So, you can measure this value for each individual vertex separately. So, what you do is, suppose you want to measure the clustering coefficient of a node, say x here, you basically look into the neighbors of x. So, say x has 1, 2, 3 and 4 neighbors. You look into the total number of connections between the neighbors of x. So, in this particular example, number of connections between neighbors of x. This is expressed as a fraction of the total number of possible connections between or among all the neighbors of x. So, this is basically the definition of clustering coefficient. Okay. So, you look into the neighbors of a particular node x. So, if you are interested to find out the clustering coefficient of x, you look into the neighbors of x. Here for this particular example, you have 1, 2, 3 and 4 neighbors. So, you can write the clustering coefficient of the node x in this particular example is, among the neighbors there are how many edges? There is 1 edge, 2 edge, 3 edge and 4 edge. So, you have 4 divided by the total number of possible edges. So, what is the total number of possible edges? It should be, so since there are 4 nodes, there should be 4 C2 possible edges. Okay. So, this is basically the clustering coefficient. This ratio actually defines the clustering coefficient of a particular node. So, in this way you can measure the clustering coefficient for each individual node in the network, and the clustering coefficient of the whole network is just an average of all the individual clustering coefficients of the different nodes. Okay. So, it is a node centric property. First of all, for each individual node you measure the clustering coefficient. Basically, for each individual node you try to estimate what is the extent of cliquishness, how complete or how cliquish the neighborhood of that particular node is. So, you try to express that as a fraction of the maximum cliquishness possible. Okay. And then this fraction can be estimated for each individual node, and then for the whole network you just have average out all the individual clustering coefficients for the different nodes. Fine. So, that is how you define the clustering coefficient of a particular network. Now, for this part of the lecture, I have shown you 3 examples. If you see in the slides, I have shown you 3 examples. There are 3 different examples where the clustering coefficient for the first example should, for that black node there in the center, should be equal to 0, because there is no edge that exists between its neighbors. Okay. There is no edge that exists between its neighbors. Okay. Fine. So, similarly, the clustering coefficient for the second example is actually 0.5, because there are 3 edges between the neighbors. Okay. There are 3 edges between the neighbors, and there could be a possible of 4 C2 edges. So, that's how you measure. Similarly, for the third example, the clustering coefficient is 1, because all the nodes that are neighbors of the black node are completely connected. Okay. That is how you actually measure the clustering coefficient for each individual node. So, this is in the next slide I actually define the formula more precisely, the same thing that I have written down in the text. So, now the interesting part is that you can measure, once you have this quantity, you can measure the extent of transitivity of the different real world networks. So, and actually that was the thing that people were trying to do in early 2001, 2002, and what they found is that, so if you look into these networks, the World Wide Web, the internet, the co-authorship network, the metabolic network, the C. elegans network, you see most of them have clustering coefficients ranging from somewhere between 0 and 1. But what is interesting to note is that networks like co-authorship network, okay, has a very high clustering coefficient. That is, these are mostly social networks which have very high transitivity. That is, the idea is that if there are a lot of mutual co-authors between a pair of scientists, then it is highly likely that those 2 scientists have also co-authored a paper. So, that probability is quite high and is close to, roughly close to 0.43 as per the table shown in the slides. Okay. So, another interesting example is this Aster network. This is again, and since this is an interesting example, I would like to take up this and discuss a bit more. So, this example actually draws from the complex system of movies and actors. Okay. So, you conceive first of all of a bipartite network, okay, where one partition is basically the movies or the movie nodes, the other partition is basically the actors or the actor nodes. Okay. Now, you have some movies and you have some actors. Now, you draw an edge between a movie and an actor if suppose this, say the name of this movie is M1 and the name of this actor is A1. You draw an edge between M1 and A1 if A1 is in the cast of the movie M1. Okay. So, this is how you construct a movie actor bipartite network. Now, from this bipartite network you can construct something called one mode projections. One mode projections. Okay. These one mode projections can be drawn again on this side, one mode projections. So, these one mode projections can be done on actor nodes as well as on actor nodes as well as on movie nodes. So, what you do in drawing the one mode projection? So, let us try to define that in the next part. So, suppose you have, so from the movie actor bipartite network, the movie actor bipartite network, you construct one mode projection, say on the actor nodes as follows. Suppose there are two actors A1 and A2, you draw an edge between A1 and A2 if A1 and A2 have co-acted in a movie, say M. Now, this graph, as you can imagine, can be a weighted graph. So, this can have a weight W, and this W is nothing but if A1 and A2 have co-acted in W movies, then the weight of the edge is W. Okay. Now, in this way you can construct a actor one mode projection. So now if you think of the movie actor bipartite network, when you are constructing this projection on the actor nodes, what is happening, if you think carefully, what is happening is that for every individual movie there is a clique imposed on this network. So, all the actors in that movie will have an edge between them because they have acted in that movie. So, that forms a clique of actors for that particular movie, and for every individual such movie you are imposing a clique on this network. So, that is why these kind of graphs are usually pretty cliquish. Okay. And that is why, as you see, the clustering coefficient of this network, as I have shown you in the slides, the clustering coefficient of this particular network, the actor network, is 0.79, which is very, very high. So, the probability that there exists an edge between a pair of actors if they have co-acted with many other actors is very, very high. So, that is what I wanted to actually point out. Okay. So, then the next thing that we will talk about is this concept of small world and the 6 degrees of separation. Fine. So, this idea is again very interesting. So, suppose, look at these slides. Suppose if I say that all late registrants in the complex networks course will be given 10 marks bonus. Okay. So, how fast do you think will this information spread? Okay. in general I would imagine that it would spread very fast among all the registrants, okay, of this course. So if that is the case, then the question is that why is it so that it spreads fast, and why is it so that it actually spreads in the first place, okay? And to show that this actually happens, this spread actually takes place, the famous scientist Milgram designed a very interesting experiment which he called the 6 degrees of separation experiment. So what he actually did was something like this. So Travers and Milgram in 1969 they designed this classic study in social science. Actually this is one of the very interesting and classic studies in social science. So what they said is that suppose you have a source, say Kharagpur, okay, and there is a stockbroker in Kharagpur who wants to send a message or a packet, okay, to some stockbroker in Kolkata, okay. So now this letter, what this person does, this stockbroker does, is forwards this letter. So he does not post this letter, okay, he does not post it to the using the usual postal codes. What he does is he passes this letter to one of his friends. So this letter actually has the name, the address, etc. of the destination, okay, of the destination stockbroker. So what he does is the stockbroker takes up this letter and passes it to one of his friends whom he believes would be knowing the Kolkata stockbroker, okay. The Kharagpur stockbroker picks up this letter, okay, and passes it to one of his random friends, right. So and then he feels that this friend might be knowing the Kolkata stockbroker and would pass it on to him. So now this friend will again pass it to some other friend of his, okay, and that friend will again pass it to some other friend of his, and in this way the chain might at some point complete, okay, leading to the destination, or otherwise it may fail. So what happened was the experiment that they performed, what came out was something like this, that if the letter was to reach the target, it would reach in roughly 6 steps. So if the letter reached the destination, it did so in at most 6 steps. But as you can understand that this is a this is a stochastic experiment and things happen by chance most of the times. So what happened was like 64 out of 296 chains actually reached the target. So they initiated 296 chains to start this experiment with, but then only 64 of them survived. Many of them dropped midway, okay. But those that survived, among them all of them reached the destination in an average of 5.2 steps. So basically every letter, or every time the letter reached the destination, it reached within 6 hops, okay, roughly within 6 hops. So this was a very interesting observation that Travers and Milgram made, and this is known as the 6 degrees of separation, and this is actually a very interesting trivia question in various quiz contests, okay. So now the idea is like, you might think like, is this all a magic by which this is happening? The point is, intuitively if you try to explain this, there is a reasonable explanation that exists. It's nothing happening by magic. There is an there can be an intuitive explanation for this, and in the next slide we will try to discuss this intuitive explanation. So imagine that you are a person in the network, okay. So think of your Facebook friends. How many Facebook friends roughly you have? So I would imagine somewhere between 500 to 1000. Let us be much more moderate. Let us take that you have, say, some 100 friends, okay, and I am assuming that these 100 friends are not connected among themselves. So you have more than that, but then say there are at least 100 who are no way connected among themselves, okay. Now these 100 friends by the same hypothesis will again have another 100 friends like this, and this will continue. So, now if you look at this tree of acquaintances or friendships, okay, this completely disparate tree where two nodes only know the parent but nobody among themselves. Okay. So, this if you grow this tree, then what you see is that within 6 to 7 steps, so if you have 100 friends in each level, within 6 to 7 steps you have, within 6 to 7 steps we have covered the entire population of the earth. Of course, I understand that there could be transitivity triangles, but what I am assuming is that there are 500 friends, and among these 500, or there are, so in many of you will have 800,000 friends, but among these there are at least 100 friends who are not connected among themselves. Okay, that is the assumption, and that is the assumption in every step. Okay, if you do this simple assumption, which I would say is a realistic assumption, and if you go by this, then at every step you spawn a bunch of new nodes, and if you have spawned until say 6 steps, you have at least like a few billion nodes that you have covered, right. So, that is how, so this is why Milgram and his colleagues could have each of the letters reach their destination within 6 steps. Okay. That is the basic idea of the 6 degrees of separation. Okay. So, then after this we will start with another very important quantitative metric that people quite often use. So, these are called centrality metrics. So, as the name suggests, you can immediately understand that centrality would indicate how central, okay, a node is in a given network. Okay. So, you want to estimate how central a node is in a given network, and as I write in the slides, so you want to estimate basically centrality in terms of these 4 quantities, these 4 P's: prestige, prominence, importance, and power. These are the 4 P's of, or the 4 pillars of measuring centrality. So, you want to identify prestigious nodes, prominent nodes, powerful nodes, and important nodes. All of them more or less mean similar if you think carefully. So, we have to have quantitative measures to identify such central nodes, and this is actually important in various ranking experiments. Because in various experiments what you want is to rank the nodes, okay, according to their centrality values. So, the more central values go at the top, the more nodes with more central values go at the top, and the nodes with less central values come at the bottom, and this ranking is actually necessary for various other applications as we shall see in some of the later part of the course. Okay. So, now if we are like okay with the philosophical definition of centrality, we have to find out quantitative measures to identify centrality of the nodes in a network. Now, one of the simplest measures that comes to one's mind would be, in the context of a network, would be perhaps the degree of a node. Okay, degree of a node. So, that is what I write in the next slide, and this is termed as the degree centrality of a node, right. So, and the definition is very simple. Suppose there is a node say A, and it has say a degree equal to D. Okay. So then the degree centrality is equal to d by capital n minus 1, where n is the number of nodes in the network. Fine. So basically what you are doing, you are expressing the degree of a node in as a fraction of the maximum possible degree of a node. Okay. So in all, a node can be connected to n minus 1 other nodes if there are n nodes in the system. Okay. So if the node has a degree d, then you are expressing this d as a fraction of n minus 1. That is what is the degree centrality of a node in a network. Okay. Now given this definition of degree centrality, we can also define something called the centralization of a network. Centralization of a network, which means the variance in degree centrality. Okay. You try to measure. So for each node you can estimate the degree centrality. Now using these values you can measure the variance of these values. Okay. And this if this variance, so this variance is called the centralization of the network. If this variance is high, this means that there are some nodes with very high degree centrality. If it is high, some nodes with very high degree centrality compared to the others. Okay. If it is low, then all degree centralities are similar, mostly similar to each other. Okay. And an example of a case where the degree centrality is skewed, that is the centralization is high, would be, if you can simply imagine, a star network. Okay, where the inner black node will have a high degree centrality, whereas the outer nodes will have low degree centrality. So this has a high centralization, whereas a line network will have a low centralization, because all of them will have almost equal degree centrality. Okay. So that's where we end this part of the lecture. Next day we will start with betweenness centrality.